Good morning, everybody. We're going to be giving everybody a few minutes to log on, and then we'll get started. So just give us a few minutes here. Good morning, everybody, and welcome to Forensic Analytical's uh, Coffee with a Criminalist, or Coffee with a Crim. This is the second of a two-part series about firearms. The first one was done a couple of months ago with firearm introduction to firearms, just what they are and how they operate. This is going to be more about firearms identification, and I expect there to be some questions. So if you have any questions, put them in the chat. I already had a couple of questions come in via email, and we'll try to answer everything that comes in. My coworker Cindy will be moderating the chat because I can't see it. So with that, let's move on. And if anybody has any questions, feel free to ask. We'll have hopefully plenty of time at the end, and I can stick around as long as people need for questions. So what we're going to be talking about is the cycle of fire, the types of firearm, two types of firearm, excuse me, two types of tool marks, how a firearm is a collection of tools, and the needs of a tool mark in firearms identification. So basics, what is a firearm? The California definition is a firearm is a means any device designed to be used as a weapon from which is expelled through a barrel projectile by the force of an explosion or other forms of combustion. So there are other things that will project a projectile downrange, but those are not firearms. Firearms include revolvers, pistols, rifles, shotguns, and machine guns. And just for a quick review, this is a revolver. It's a handgun designed to be fired from the hand. It has a cylinder. So this is the type of firearm that will not leave ejected cartridge cases at the scene, but we might still be able to find some on a suspect or in a suspect's residence or vehicle where they may have reloaded. This is your typical pistol. This is a Glock pistol. It's also designed to be fired from the hand. The slide will go back and forth as it's being fired, and that cycles the weapon. This is a rifle. It's designed to be fired from the shoulder. The shoulder, the buttstock ends up right here, and it's a longer firearm. It's more accurate over longer distances, and that it's designed more for hunting than a handgun is. A shotgun is somewhere in between. It's also shoulder fired. It does not have it has a smooth bore, and that's the difference between a rifle and a shotgun, basically. And the shotgun will fire more than one projectile at the same time. So you can hear the term bird shot. Those are fine pellets, or you can have something that's like a double-aught buck, which is what law enforcement tends to carry, and that will fire 8 to 9 38 caliber pellets at the same time. You can also fire a slug, which is a single projectile that will come out of the barrel. And shotguns can also be less than lethal. So they can be a beanbag round or a pepper spray. This is a list of items that are not firearms. because they do not use combustion or an explosion to launch their projectile. So how does a firearm work? Let's start with the ammunition. This is a cartridge, not a bullet. It is a cartridge. Also, in military terms, it's a round. So you can hear cartridge or round used interchangeably. It is unfired and all of the components are still there. So here's a cutout of the first, and we can see what it looks like. So you have your cartridge case, which is the metal object that holds everything in place. That's basically right here. At the base of the cartridge is a primer. This is a shock sensitive explosive. There's a hole from which this fire then goes and lights the smokeless powder. As the smokeless powder burns, the gases expand and it projects the bullet through the barrel and downrange. And the cycle of fire is basically how the firearm operates. And I'll go into each one in detail. So this is a pistol. It's basically a Colt 1911 model. And the reason why I'm using this as an example is at my previous laboratory, we had one that had cutouts. And so you can see how the firearm operates internally. So the first thing is loading. You take your magazine with cartridges, put it into the magazine well. And if you look up here, you'll see a little silver object. That object is the cartridge at the top of the magazine. So as the slide gets pushed forward, it'll strip this part of the slide will hit the top of the magazine, the top of the cartridge and push it into the chamber, hence the term chambering. So the chamber is the back portion of the barrel, which is slightly larger than the barrel, and it fits the entire cartridge in there. So the cartridge gets pushed into it, and this is an example of how it does it. And as it goes forward, now the cartridge is level with the barrel and ready to be fired. As you can see in this case, the hammer is now cocked, and as soon as you push the trigger, the hammer will go forward, hitting the firing pin, which will then hit the cartridge. So here it is, the cartridge in the chamber with a cutout. And you can see there's a hole on the breech face where the firing pin will come through. And there's a tool, an extractor, that'll interact with the cartridge that will help pull it out later. So this is what it looks like. And here it is from the other side. The extractor is right here, interacting with the groove on the cartridge. And the firing pin goes through here, and it will impact the primer, which is yellow. So once it's fired, you can see the bullet is no longer attached to the cartridge. The bullet has gone downrange, and there's a lot of pressure developed on the cartridge that is now pushing against the slide. That will start moving the slide backwards, and the extractor will pull the cartridge case out of the chamber. And this is what that looks like. And there is a piece of metal at the back of the frame, basically, that will interact with the cartridge case eventually. That is the ejector. So as the cartridge is getting pulled back, it will eventually hit that ejector, which will push it out of the firearm. So this is an example of what that looks like. The ejector basically is this piece of metal right here, which pushes the cartridge case out, and it rotates around the extractor. So some theories on firearms and tool mark identification. It's a scientific discipline that is concerned with the identification of a tool mark to the specific tool used to make it. Firearms is just a specialized area of tool mark identification, which deals with firearms, which is just a collection of tools designed to work together. The principles and theory of the science behind firearms and tool mark identification are the same for both areas. So what is a tool, you may ask? A tool is the working surface of any object that marks another object when in contact. And the tool is the harder of the two surfaces. So here's some examples of tools. You got knives, scissors, screwdrivers, hammers, bolt cutters, pliers, firearms. But a good example would be a knife. So the knife is the tool cutting through a slice of cheese. As everybody has probably observed, especially if you're using a serrated blade, when you cut off of a slice of cheese, you'll see the blade marks on there. So there's two types of tool marks: impressed marks, which are that come together at a 90-degree angle, sort of like clapping. So examples of those would be a hammer on a nail, animal tracks in mud, or handprints in cement. We often think of cement as being solid, but at some point when it's still wet, your hand is actually harder than the cement. So your hand is the tool that is leaving a mark in the cement. So here's a not so typical hammer. Usually hammers have round heads, but this is one with a square head, and it's probably one of the ugliest hammers you'll ever see in your life. This is what the working surface of the hammer looks like. This is the impression of that what that hammer leaves into a softer material, and I'll go into details about this later. The other type of tool mark is a striated tool. This is one where the tool is moved across another object, and by moving it across, the surfaces that are interacting are a 90-degree, and so they leave marks that you don't expect to be able to be reproduced easily. Examples of that are scratch from a screwdriver, baseball player sliding into home plate, or a scratch on a car from a shopping cart. So here's an example with a screwdriver, typical flathead screwdriver. And you can see here that there are marks that are parallel marks, but they're going perpendicular to the blade, or to the shaft. And this is the mark that is left by that. And I will zoom into that sooner. And you can see that these marks are not going in the same direction as the marks on the actual screwdriver. Because what's happening here is the imperfections on the tip of the screwdriver are making these marks. And that's what we are looking for, not necessarily the marks that are manufactured into the tool. So a firearm, like I said, is just a collection of tools. Here we are back with our cutout. These are the tools in place. And then this is the tools that leave marks on cartridges and bullets. So you got your barrel. This will leave marks on your bullet. The chamber, which could leave marks on the cartridge case. Your breech face, which will leave marks on the cartridge cases. Firing pin, extractor, and ejector, which all leave marks on your cartridge cases. And this is how they look within the firearm. The barrel and the chamber are down here, and then the other parts are basically on the back of the slide. The breech face is a very important surface. It's the smooth surface that's that gives support to the cartridge. So when the cartridge is fired, there's a lot of pressure that goes both forward down the barrel, projecting out the bullet, and the same amount of pressure is pushed towards the back of the slide, which then operates the semi-automatic pistol or firearm. That hole is the firing pin aperture, and that also leaves a mark on the cartridge case. And this is what it looks like in an actual firearm. You've got your firing pin aperture, your firing pin, your extractor, and the ejector will be right here. And typically in a semi-automatic firearm, as it's fired, the slide moves backwards and it ejects your cartridge case, which is right here. And it typically goes back into the right in relation to your ejection port. So the ejection port is right here, and it's going back into the right. But if a firearm is tilted, it could be in any direction. The ejection pattern will go straight up, to the left, or straight down, just depending on how the gun is oriented. So these are just some stylized breech faces with the associated ejectors. So they can come in different shapes and sizes. The breech faces can be parallel, they can be perpendicular, they can be random, circular, or half circles or unhappy faces. And this is what it would look like on the actual cartridge case. Everything is inverted because it's an impression. And the ejector marks can be rectangular, round, triangular. And as you can see in here, they don't necessarily replicate completely. So like this rectangular one here looks like a triangle because only part of it actually hits and interacts with the cartridge case. This is a diagram showing the typical marks on a cartridge case. The breech face is the one that are kind of the most important marks because they're easily seen. They have class characteristics that we can look at, and I'll talk about that in a minute. But these are the marks that we tend to look for on cartridge cases. So here's an example of an unfired cartridge. And as you can see, there's already some marks here. This is the primer, which we mainly look at. And then there's another mark right here. That's a brand new cartridge, unfired, not cycled in a firearm yet. It's just straight out of the box. But there are tools and deformities that are found on just about everything. So this is what it looks like once it's fired. You have your firing pin impression. You have your breech face marks, an ejector mark, and an extractor mark. So the first things that we look for are caliber. Caliber is basically the diameter of the barrel. You would think this would be straightforward. You've got, several different markings, sizes, but no, things get a little bit complicated. For instance, let's take 38 caliber. A 38 caliber and a 9mm caliber are the same caliber. But within that caliber range, you can also have a 380 auto, a 357 Magnum, and a 38 special. So all of those barrels are the same size, but the cartridges are different, so they don't fit into one another. And then on the bottom here are some examples of rifling. The barrels are rifled. Basically, cuts are made into the barrel, which allow the bullet to be stabilized. So if you think about a football, if the football is thrown end over end, it's not very stable, it doesn't go very far. Same thing would happen with a bullet. So manufacturers put rifling into the barrels, which helps stabilize the bullet, and it'll go a longer distance more accurately, similar to a tight spiral on a professional quarterback who can throw it 50 yards. So here's some rifling. So if you look at the top image, you've got 4, 5, 6, and 6. The cross sections look like this, but you'll notice that on the 6s, something looks a little different between these two. It's the rotation. So the first 3 have a right orientation, and the fourth one goes to the left. So this is what it looks like in the cross section, and on the bullet, you'll see these go to the right, and this one goes to the left. And this is what it looks like on actual bullets. So just by looking at these bullets, there are some class characteristics that I can already tell. This bullet right here is elongated, and it's a rifle caliber. These two look like they're about the same size. This one is lead and has cannelers. So this tells me that this one is a revolver caliber. This bullet is a little bit bigger than this one. It's got a truncated cone shape, which typically is a nominal 40 caliber. This bullet right here has a round nose and it looks bigger. So knowing that this is a 40 caliber, this is most likely a 45. So now this is going to the right, this is going to the right, this is going to the right, and this one's going to the left. So one of the things that just by seeing this bullet with a left hand twist that looks like it's got 6, that tells me that it's most likely a 1911 type firearm. So just a reminder, forensic tool mark identification is a scientific discipline that is concerned with the identification of a tool mark to the specific tool used to make it. However, since we cannot examine every single tool and compare them side by side, it's made to a practical exclusion of all other tool marks. This means that the likelihood another tool could have made the mark is so remote as to be considered a practical impossibility, but we can't say all other tools are excluded. So for an identification, 3 criteria must be met. The class characteristics must be the same. There can't be any subclass influence, and sufficient agreement in the individual characteristics must be present. So class characteristics are measurable features that are imparted by the manufacturer. So they might want to have a 5 right or a 5 left. That is up to the manufacturer, and the width and size of those rifling impressions are what they require. The shape of their firing pin aperture hole has to be a certain size for their firing pin to fit through. So they have go, no-go tools that it has to fit in order to go on in the line and be made into a tool. So for instance, here's an example of, let's say you're renting a vehicle and all these vehicles are parked on the lot, and you have to find the one that you rented. So you know you got a car. So you can eliminate the motorcycle right off the bat. You know it's not a truck. So all the trucks are eliminated. It's 2 doors. So all the 4-door vehicles are eliminated. It's a coupe. So all the convertibles are eliminated. Too bad because the weather's really nice right now. And you know your vehicle is white. So of the entire parking lot, you just limited yourself down to 3 vehicles. And because on the key fob probably has a license, so you can go to the license and figure out which of these 3 cars is the one that you're looking for. That would be the individual. But if it's your own vehicle, you might know that you have a scratch here, a dent there. So instead of looking at the license plate, you can just go find your vehicle based on the scratches and dents that you have on yours. That's what we do in firearms comparisons and tool mark comparisons. We can eliminate, we first look for the class and then look for the subtle markings within that class that are not intended to be manufactured. So individual marks are random imperfections on the tool surfaces. They're caused by damage to the tool itself or the tool making the tool. And they tend to be unique to that tool and distinguish it from all others. So back to that ugly hammer. So the manufacturer of this hammer intended it to be square of a certain size. All of this other stuff, that is most likely due to wear and abuse. So looking at that impression of this hammer, you can now see that these marks right here translate right here. These marks translate right here. This mark translates to that mark right there. And then this large imperfection translates to that imperfection. Sorry. You can also see that this general shape right here there's a general shape like that up on the top where this little squared area corresponds to the squared area. So subclass are marks that are in between individual and class. Basically, as the manufacturer is making a series of tools, something could happen to the die or the tool that is cutting the finished product. And so when that happens, until somebody notices that there's an issue, a group of items will be made with similar marks. So let's say hypothetically you're making a firing pin. This firing pin has a rounded tip. And so the way it's manufactured is it is turned and a knife blade comes in contact with it. So as it's being cut, chips will form that might cut the actual blade. And so if you look on the surface, this is what the firing pin will look like. And you can look at this and go, wow, there's a lot of marks here that you could use. All of these wonderful lines. But because some of these lines go all the way around, those are potential subclass. So those can be used to orient yourself and look for other marks, but they can't be used for an ID. For the ID, you have to start looking for these little subtle things that are found throughout. And that's these marks right here. So that's what you're looking for the ID. These are potential subclass. So for tool mark agreement, a tool mark is a dynamic process. The materials can change. For instance, you could have a lead bullet versus a copper jacketed bullet. Those will mark differently, even though they're fired from the same firearm. You could have a brass primer or a nickel plated primer. Those will mark differently. And you can have your first shot look a little different than the 10th shot because there's been a temperature difference. The first shot is fired when the firearm is cold. And as more and more shots are fired, it heats up. And so it could leave slightly different marks. So no tool marks are ever exactly the same. And sufficient agreement is deemed to be sufficient based on the correspondence of a pattern or combination of patterns. And the agreement exceeds the best agreement demonstrated between known non-matches and is consistent with agreement demonstrated by known matches. So known non-matches are when you take two tools that you knew were manufactured at different times. The worst case scenario are consecutively manufactured tools because these are made one right after the other. And so there should have the least amount of difference between them. And there have been studies done with consecutively manufactured tools, and firearms examiners and tool mark examiners can tell the difference between them. So the foundation for tool market identification is basically examining and reviewing studies based on test marks from consecutively manufactured tools. Studies have been done with barrels, slides, firing pins, extractors, ejectors, and screwdrivers. And in all of these cases, examiners were able to tell the difference of tools that were made right after one another. It also entails doing examinations and reviewing studies based on class-matched firearms. So that would entail, example, at the lab, you might have 5 Glock pistols, and you do studies with those during your training to determine which cartridges and bullets could have been fired from the different guns. And these are, again, worst case scenarios because they are similarly manufactured. The marks, all of the class characteristics will be identical, and you're just looking for the individual marks. And this gives you, allows the examiner to establish a best possible agreement found in known non-matches. The other theory that is out there is consecutive matching stria. This is what I use and my coworkers use. Stria is basically a linear mark or a scratch made by moving a tool across a surface. Matching stria agree in their spatial orientation, width, and morphology. Consecutive matching stria are groupings of matching stria. This is a theory that was originated by Biasotti in 1955 and formalized in 97 by Murdoch. And it's basically, and working between has provided an empirical data for the theory. So basically what we look for is in 2D striations, which are very, very flat, you look for two groups of 5 or one group of 8. And in 3D groupings, which are typically seen on firearms, you're looking for two groups of 3 or one group of 6. But in all cases, subclass must be ruled out. So here's an example. So these are lines that are, you can see some correspond, some don't. But right here we have a 6X. 6 of these lines match up very well. Here, they just don't, the green ones don't line up at all. The blue ones line up, but their sizing are different. And here there's a break, so you can't count that. And then the purple ones are back to being 3X. So between the 6X and the 3X, even though there's some differences in between, this would be a match. So here's some examples of comparisons. So we use a comparison microscope, and this is basically what we use. It is two objectives, or excuse me, two scopes that are linked by an optical bridge, so that when we look through the eyepieces, this is basically what we see. You can see what's on the left stage and on the right stage and compare the objects together. So this is an example of comparison of a bullet on one side and a scale micrometer on the other, or stage micrometer, excuse me. We have comparisons between, cartridge cases. So this is what we're talking about. We're looking for class differences. So the one on the left is a test fire. It has a rectangular firing pin aperture. And the one on the right has a round hemispherical aperture. This one is relatively smooth. This one has round marks from the breech face. So this is a class elimination. Both of them are the same caliber. They're both 9mm. However, one is rectangular aperture, one is round. It's a class elimination. You're done. You don't have to do any further work. On the other hand, if you're looking at two things that look similar, now you have to zoom in and look for things that might be different. So in this situation, you're looking at the breech face. You've got the markings right here and right here. The firing pin is the same shape. You might even be able to see some of the marks in the firing pin. But you can also see these striated marks. The striated marks, because of the way they're made, you don't expect there to be subclass. So therefore, those are the marks that are better to use for identification purposes. And you can see here how the right stage and the left stage, they line up like a barcode. And this one's shifted a little bit, but you can still see how they line up fairly well. And there might be a couple of differences here and there, but they line up well enough that this is an ID. And these are test fires. So what you're looking for here is how well they match up to one another and what to look for when you're actually looking to compare them against evidence. Bullet comparisons, same thing happens here. You can see that the groove impression here and the groove impression here are different sized, and the land impressions are different sized. This one is smooth, this one is striated. So again, these are not fired from the same firearm. It's an elimination, you move on. Whereas in this situation, they look similar. The sizes are the same, the class characteristics are the same. So now you have to start zooming in and looking for the striated marks. So that's where these are right here. And these are test fires and they're pristine. These are actual evidence not so pristine. So those subtle marks are now could be even more subtle because the bullet has gone through something and it could have abraded it. So here's what these look like, and they can also be deformed. So again, you can see in here all of these striations match up like a barcode, and you can do the count on these and figure out whether or not they're good enough to be called an identification. So in summary, we talked about the cycle of fire, impressed and striated tool marks, how a firearm is a collection of tools, and that in order to make a firearm identification, you need the matching class characteristics, sufficient agreement in individual characteristics, and no subclass influence. So if anybody has any questions, please feel free to do so. I got 2 questions earlier, and I will answer those right now. The first one is, how accurate are NIBIN leads alone? If a single casing ejected from an unknown firearm is submitted into NIBIN, is it common for the tech to expect many 10 plus potential leads to be returned? Is it common to limit NIBIN searches to regions in order to limit the potential of too many leads for the results to be helpful? So the answer to that is NIBIN leads are okay. The image quality is relatively mediocre, which is why they require it to be examined on a comparison scope. The algorithms are such that you basically are comparing similar images, and they send you the top images. It's a long list of images, so yeah, well over 10. And depending on your laboratory policy or agency policy, because some are done by the police departments as well, they can limit it to 10, 20, 30, or 50 that you have to look through and compare all of those. And based on the algorithms, hopefully your hits are actually found within your range that you're searching. Let's see. The region is always limited because otherwise you would get comparisons to firearms that there's no need for you to compare. For instance, if we're in Northern California, we don't need to be comparing guns that are in Florida. And so that it helps with the algorithm because it limits what they're actually searching, but it also keeps your database from getting massive. This can be an issue every once in a while because if a firearm moves from, say, Southern California to Northern California, we wouldn't find that hit. I had an example where we knew that a suspect drove across country from Georgia and used the firearm in Northern California. So we figured out what route he was on and ended up searching against all of those regions just to make sure that no other crimes were committed. So hopefully that answered that question. Another question is, can you help with challenge to tool mark evidence under Sargon? That government firearm examiner's testimony that the cartridge cases are a match is without a reasonable basis. And then C, TID case. Are you familiar with studies? Thanks. So the Sargon case is basically a follow-up to the gatekeeper role of the courts. In that situation, I think it limited what the person what the expert was able to do because of what some of his testimony wasn't based on science. So as long as it's based on a science, we're doing scientific research that lays the foundation for what we're doing. What we're testifying about is true. The TID case, from my understanding, was depublished because I thought it was a technicality that they had discussed some stuff in the 402 hearing that didn't get brought up into court, but then under review, that came back. So that was the issue in that case. I'm not an attorney though, so I don't know if that is exactly what happened. And a lot of questions are about PCAST. There's been a lot of research done since PCAST to show that the the foundation for firearms and tool marks is correct. And a lot of the research is being done by NIST, who are able to use instruments that are too expensive for most laboratories to have, and they are definitely showing that the identifications are able to be made. So hopefully that answers questions, and if anybody has any, please feel free to ask away.
Thank you, Alex. I don't see any other questions just yet. This is Cindy, everyone. Thank you, though, and I appreciate everybody putting in those advanced questions. Super helpful to have them in advance. But I don't have anything else, it doesn't look like.
And if anybody thinks of anything they want to ask later, my email is up on the screen, and feel free to contact me.
Great. Thanks, everybody, for joining us today, and hope to see you at our next Coffee with the Crim.